Hello everybody. In this video, we're going to learn about our last differentiation rule, and that is called the chain rule. So far, we have about a handful of differentiation rules, but they are sort of limited in what they can allow us to differentiate. So the chain rule allows us to find derivatives of functions that are compositions or composite. So just to contrast with what we have already, so far we know derivatives of essentially two basic functions. So the first function that we know the derivative of is a function that's constant. So remember, this d over dx means the derivative of what's coming next in the brackets. And the dx in the bottom here tells us that x is the variable. So the derivative of something that's constant, right, this is equal to 0. So this is the constant function rule. We've been using this so far. It's the simplest kind of function that we can have. And this was our first rule that we talked about. The second rule that we had is called the simple power rule. The next most basic function you can have is just a simple power of x. So the derivative of x to a power, how you differentiate that is bring the power down, multiply, and then subtract 1 from the power to get a new exponent. Then we learned how to combine these kinds of functions together with addition, subtraction, multiplication, and division. So we next saw what happens when we multiply a function by a constant. So this is called the constant multiple rule. So if we take the derivative of some constant times some variable stuff, so I'll just write f of x, could be anything, that constant just multiplies by the derivative of whatever the variable part is. Then we saw what is called the sum and difference rule. So this allows us to differentiate two or more things added or subtracted together. It works out as nicely as we could hope. The derivative of a sum or difference is the sum or difference of the derivatives. Then in section 2.4, we saw how to handle products of variable things and quotients of variable things. So we learned about the product rule. So here is if you are taking the derivative of a product of two variable things, we leave the first one alone and multiply by the derivative of the second. Then we add the second one multiplied by the derivative of the first. The quotient rule was our last rule that was also in section 2.4. It's probably our most complicated derivative rule. So if we're going to differentiate something over something else, I'll use n over d for numerator and denominator, where the n and the d both again stand for things involving x or a variable. This is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Now that's a hard one to memorize. So we have a little mnemonic that I think I mentioned in that video. Low d high minus high d low over low squared. So I know that d and n maybe don't really stick, but I think that, I don't know, that kind of rolls off the tip of your tongue if you say it a few times. It's pretty easy to remember. Compositions or composite functions, this is a way that we can combine functions together. That's a little different than, we can't compose numbers together. But with functions, it makes sense because we have an input and an output. So this is, in fact, our very last differentiation rule. And it is for composite functions or compositions. And it is called the chain rule. That's a general way of describing this rule. We're going to really look at this rule in the specific context where we have a certain kind of composition. And in this context, we can call this rule the general power rule. So we had before what's called the simple power rule, which handles powers of x only. X is the base, that's it. With the general power rule, we're going to be able to find the derivative of things that are raised to a power that are more than x. Like maybe, x squared plus 1, or I don't know, 3x minus 4, something like that raised to a power. So just to contrast the kinds of things that we could differentiate without the chain rule and things that we can now differentiate with the chain rule once we learn what the rule says. So here's a few examples. Without the chain rule, we know how to differentiate something like x squared plus 1. With the chain rule, we will be able to differentiate something that looks like x squared plus 1 to the 100th power. Now, if this were to the second power, we know that we could expand this out by FOILing and then use our simple rules to differentiate. But no one wants to sit here, not even me, and expand all of this out to the 100th power and then find the derivative using our simple rules. So there's a much easier way to do this, and that will be with the chain rule. Here's a few more examples. Y equals 3x minus 4. We can differentiate that. But what if we were looking at a function where we had the square root of 3x minus 4? We know how to differentiate the square root of x as rewriting that as a power, but now we have something as the base that is more than x. We don't have a rule for this yet. Yet another example, how about y equals 4x cubed minus 10x? Again, this is a polynomial. We have rules to differentiate this, but we don't know how to differentiate something that looks like 4x cubed minus 10x to the negative 1/3 power. We just don't have a rule for this. Last but not least, we've got a function here that we could differentiate using the quotient rule. X plus 5 over x squared plus 2. We could differentiate this using the rules we have already, but what if this were raised to, I don't know, the 7th power? We don't have anything that can help us find the derivative of this function. So this is really going to expand our repertoire of what we can find the derivative of. It's super exciting, and it's actually fairly straightforward. The key idea to using the chain rule is to be able to recognize what is the inner function in the composition and what is the outer function in the composition. And if you can do that and you know the formula for the chain rule, then you will be good to go for using it. Okay, so again, the key idea for using the chain rule is to recognize what the inner function is and what the outer function is. So let's take a sec to do this with these particular examples here. So the inner function in x squared plus 1 to the 100th is the x squared plus 1, and that's being plugged in to the function that raises things to the 100th power. So the inner function here is the x squared plus 1. You don't have to get too fancy with the notation or anything, just try to draw out what's the inner and the outer. The function that this x squared plus 1 is being plugged into, again, is the function that raises things to the 100th power. So we would represent that as x to the 100th. And so we can represent our function that we're looking at here as what we would get if we plugged this expression in for x into the outer function. So this is what it means to have a composition. You put one function into another. In our second example here, we have the square root. That's the outer function. And what's being put into the square root function is 3x minus 4. So here our inner function is 3x minus 4. And our outer function is the one that square roots things. So the square root of x. Take a sec to pause this and see if you can figure out what the inner and the outer functions are for our last two examples. In our third example here, right, we have something that is raised to the negative 1/3 power, but what's inside is another function itself. So in this case, right, our inner function is the 4x cubed minus 10x, and that's being put into the outer function that raises that stuff to the negative 1/3 power. Now don't get too hung up on the x's being in both of these functions here. I know it's hard, but we want to think about the x as being like a general placeholder for things. And what that's a placeholder for can also be stuff with x. So just think about this whole thing here, right, being substituted in for x. And when you do that, you'll get the result of what we have for our function. Okay, for our last example here, we've got an outer function that raises stuff to the 7th power. And what's being put into that is the inner function, that's this quotient. Okay, so here we have an inner function that's x plus 5 over x squared plus 2, and an outer function that raises all of that stuff to the 7th power. Now notice that in each of these columns separately, here, the inner column, and here, the outer column, we can actually find the derivative of each of these pieces separately. Now that's going to be important because the derivative of the whole thing, the composition, is going to be related to the individual derivatives. Okay, so notice here that we can find the derivative or differentiate each column on its own. The chain rule is what is going to bring it together. So here is how the chain rule goes. And if you don't know it, you're gonna have a bad time because it is really prominent. There's a lot of functions that are compositions like this, many more than just ones that are more simple. So this is our last rule, but it's also in some ways one of our more powerful rules. So here's what it says in general. Okay, the chain rule is a very general statement of what we will in a minute more specifically talk about in our general power rule, which are all the examples that we just saw up above. So what the chain rule says is that if you have two functions, they're both functions of x, then if you were going to compose them, okay, so you might want to maybe go back and watch our video on function composition, which was in chapter 1, I believe. It's not too important for us to be able to compose functions, but the notation you might need a little bit of a refresher on. So here is how we write function composition, one way at least. So into f of x, we're going to put the input g of x. So it's f of g of x. So the input into f is the g of x. So in other words, here, the g of x is the inner function. And the outer function is the f of x. If we're going to find the derivative of this thing, here is how we handle it. So we go from the outside in. So we look at the derivative of the outer function. Well, that would be f prime, but we leave the inside function the same. So it's f prime of g of x. Okay, so so this is the derivative of the outer function, leaving the inner inside. So the outside has a derivative, but the inside also has a derivative or its own rate of change. And the way that that gets handled with what the chain rule says is that we end up multiplying by the derivative of the inside. So this all gets multiplied by g prime of x. Okay, the derivative of the inside, or the derivative of the inner. Now I know at this point that this might look very complicated. I think as you go through some examples, it becomes a lot more easy to see in like your math eye. And in particular, we're going to, like I said, look at this in a very specific case. So when we have a certain composition where the outer function is something that raises something to a power, like in our examples up above, then what we get is something called the general power rule. There are other times where we will use the chain rule later on in chapter 4 when we're going to look at exponential functions and logarithmic functions. But for now, the only kind of function that the chain rule will apply to are functions that look like something to a power, where the something is more than just x. So let's have a specific formula or statement for the chain rule in this context. So specifically, when the outer function is a power function, we get what's called the general power rule. So here's what it says. If we're going to differentiate a function of x raised to a power, so I'm going to use that function of x instead of f of x. I'm just going to write a b here, b to a power. Okay, but the b, I'm just kind of using that as a base, but this is really representing a function of x. So we could use f of x instead, but normally our whole function is called f of x, so that can get a little confusing. So I'm just going to use b for base, but really it stands for a formula or a function of x. So our outer function's derivative is the b to the power. So when we differentiate that, we bring the p down and multiply. Then we subtract 1 from the exponent. Right, that would be the derivative if we have something to a power. So there's the outer function's derivative. Then the inner function is the b, the base, the stuff that's raised to a power. So what we'll do is multiply this whole thing by the derivative of the base. And that would be by b prime. So this rule is, like I said, very useful and very important. We will use this a whole lot. Here's another way that you could think about this power rule. Kind of a weird thing to think about in this way, but here's a comic from a lady who studies math and is like a mathematician and stuff. She says she learned the power rule by differentiating the mother and leaving the baby inside. So if you think of the mother as like the outer function, the baby is the inner function, it's inside. And then you differentiate the baby, the inside, and multiply in order to use the general power rule or the chain rule. Someone in a previous class talked about it as like your coat being the outside and the inside being you. So I don't know if you have any other things that you come to mind when you're thinking of this, whatever works for you. Feel free to think of it that way. So let's look at our first example. Let's find the derivative of y equals 1 minus 3x raised to the second power. We're going to do that with the chain rule, or without the chain rule first, and then also with the chain rule, just so we can see that we'll get the same thing. So without the chain rule, this just means using our old ways that we know how to differentiate things. So to differentiate this without using the chain rule, we would have to first FOIL this out, right? We've done this before in a previous, in the beginning of this chapter. So we would need to first FOIL. Okay, so we've got 1 minus 3x squared. So that's 1 minus 3x times 1 minus 3x. When we FOIL that out, we get 1 times 1, which is 1. We've got 1 times negative 3x, which is negative 3x. Then we've got negative 3x times 1, which is negative 3x again. And then we've got negative 3x times negative 3x. That's positive 9x squared. So combining some like terms together, we've got 1 minus 6x plus 9x squared. Then we can find the derivative. So write diff here for differentiate. So we'll find y prime. The derivative of 1, that's a constant by itself, that is 0. The derivative of 6x is just 6. So we'll have minus 6x or negative 6x. And then we'll add the derivative of 9x squared, which is 18x. Okay, so here's what we know what the derivative is for sure, right? I hope, trust this, that this is in fact the derivative. But let's see with the chain rule that we'll get the same thing. So again, the key to being able to use the chain rule, or the general power rule in this case, is recognizing what the base is. That's really it. So it's always just the thing that's raised to the power, right? What we have here is some stuff, 1 minus 3x, raised to a power 2. So if you look back at our general power rule formula, that's all we really need in order to use this formula. Right, our power here is 2, so that can be taken care of. The base 1 minus 3x and its derivative we can find. So to have a little structure on this, I usually just write down what the base is underneath. So again, it's just all of this stuff that's raised to the power. Now I know in the formula I'm going to need the derivative of this, so I'm just going to figure out what is that separately. 1 minus 3x's derivative is negative 3. Okay, then we have this 2 up here, and that's the power. So what we're thinking of is like, okay, we've got some stuff to the second power. How would we differentiate that? Right, if we have something raised to the second power, then what we would do to find the derivative, it'll look like 2b to the first. We'll subtract 1 from the power. But then we have to multiply by the derivative of the inside. So that'll be times b prime. I'll make that a little curvier, right? We got b to the first and b prime here. Okay, so if we're going to find the derivative of the whole function, y prime, the 2 comes down and multiplies, just like normal. But now look here, the base, b to the first, in the formula here for the general power rule, the base stays the same. We only differentiate the inside at the very end. Okay, so the base is going to stay as 1 minus 3x, and then we subtract 1 from the power, so it'll be to the 2 minus 1. Then we multiply by the derivative of the inside, b prime. So we saw that that is negative 3. Okay, so just to be really, really clear here, right, what's happening is here, this is 2b to the 2 minus 1. The base stays the same, always. Then we multiply by just the derivative of the base. And that's pretty much, that's it, right? From here on out, we have to simplify. So, to the 2 minus 1 power, that's just to the first. So we can just write that as 1 minus 3x. This doesn't look like our derivative from part A, but if we distribute things, let's see what we get. So let's do the 2 times the negative 3. That's negative 6. And we can distribute the negative 6 inside. And we'll get negative 6 plus 18x. There we go. There it is. It's the same as before in part A. That makes us happy. Right? No matter how you do a math thing, it's got to come out the same, no matter which route you take. So I hope you can trust the chain rule or the general power rule. So that's our introduction. Tune into the next video for a lot of examples using this and combining it with a lot of our other rules like the product rule and the quotient rule.